So number 7. So this says, do you see? So the first step here is I'm going to take whatever my given factor is. In this case, that's x plus 3. Set that equal to 0 and solve. So when I subtract 3 from both sides, I get negative 3. That negative 3 then is going to be on the outside of my synthetic division. The numbers on the inside of my synthetic division setup are the coefficients for the polynomial I'm trying to factor. So 1, 5, 5, 1, negative 6. So far, okay with the setup? Now we're going to go ahead and do the synthetic division. So the first step is it down. And then we're going to multiply the number on the outside to the number underneath and write that answer in the next open spot. So negative 3 times 1 is negative 3. And then we add down. Megan. Oh, yeah, I guess I just wrote down the wrong thing. Thanks. And now I'm just going to repeat that same process until I filled up all of my spots. So negative 3 times 2 is negative 6. I add down, I get negative 1. Negative 3 times negative 1 is positive 3. I add down, I get negative 2. Negative 3 times negative 2 is positive 6. I add down, I get 0. Which is what I should be getting if something is a factor. The remainder should be 0, so that last number should be 0 when you're told something is a factor. Now, what this piece of information tells me is this polynomial factored, or at least a partial factoring of it. Because my remainder was 0 when I divided x. I know x plus 3 is a factor. Okay with that? My other factor is going to be the quotient from the synthetic division. And that's what these numbers are going to tell me. So remember, the way these numbers is we start at the right, the constant, and then the x coefficient, the x squared coefficient, the x cubed coefficient. So that gives me my other factor. So far, so good. Now we have to check to see if we can do any more factoring of these two pieces. So x plus 3 we know we can't factor anymore because it's linear. X cubed plus 2x squared minus x minus 2 has 4 terms. So if I go back to the factoring tree, I can check to see if I can factor that. Okay? So I'm returning back to the factoring tree stuff that you would have done like in the first half of this assignment. So for 4 terms, we would try grouping. So let's do that. So from the first group, I can take out. From the second group, I can take out a negative 1. And that leaves me with x plus 2 times. Still doing okay, Hallie? It's okay. Ben, how are you? Okay. Let me know if I go too fast on something or do something you're not sure about. So the x plus 3 is still here. That's still kind of, we know that can't factor anymore. We established that earlier. The x plus 2 we know can't factor anymore because that's linear. but we still need to check the x squared minus 1. That you should recognize as like a chapter 4 factoring question, right? That's a difference of 2 squares. So we can factor the x squared minus 1 into x. And that is our best we can do. Since everything is linear, we know that we can't factor any of those anymore. So the big takeaway here that you should be taking from this problem is this synthetic division step we're going to use until we can get back onto the factoring tree path where we can get something we can use our factoring tree methods on. So really can't ever forget about that factoring tree part. Like that's still going to be a piece that we're going to need to use. What we're doing is we're extending the stuff we can use the factoring tree on, because now if we do some of these synthetic divisions, and maybe we can get to a piece we can use the factoring tree on. You know what I mean? So that's the idea here. And we'll extend that idea here some more today in the lesson, but I don't want to get too far down that road because I assume there'll be a few more questions about things that I want to make sure we address before we start moving forward. But that's the path we're going to be heading down today, is to kind of formalize that process a little bit more.
Cool.
Yeah.
In your answer, I'm more confused where you got that x plus 1 from.
So if you look at the previous line, x squared minus 1,
yeah.
That's a difference of 2 squares that factors into
okay.
x plus 1, x minus 1. No problem. It was an easy explanation, so no big deal. Should we do another, Megan? 8? Sure. So 8's by far the worst one, and it's mostly just the worst one because of the factoring tree piece at the end. But we're going to start it the same way. So I'm going to start by taking the factors to 0 and solving. And then I'm going to set up my synthetic division. But as I go to start writing in my polynomial here, I notice something about this polynomial that's different than the previous one that we just worked on. Well, the degree is bigger, duh, but something beyond that. If I look at the individual terms of this polynomial, I have x to the 7th, x to the 6th, and then I go to x to the 4th. What did I skip? Yeah, so I'm going to mean to make sure I put a 0 in my synthetic division setup there. And we do the same thing there at the x squareds, right? Where we skip the x squareds. So when we set up our synthetic division, we need to make sure we include those zeros. You will not get there's no way to recover from not including those zeros unless you start all the way back over again. Please make sure you're there and looking for any missing terms when you start setting up your synthetic division. I know it's easy to forget to do that, but it is really critically important that you don't. Like, things will not work if you forget to do that. So if you encounter a situation where the synthetic division doesn't work and you'd expect it to, that's like a likely culprit is you forgot a 0. Megan, are we good so far? Okay. So we'll start by bringing the first number down, and then -3 times 1 is -3. Add down to get 0. -3 times 0 is 0. Add down to get 0. -3 times -7 is 21. Add down to get 0. -3 times 0 is 0. Add down to get 0. -3 times 0 is 0. Add down to get -8. -3 times -8 is 24. Add down to get 0, which is what we expected. Since we knew that x plus 3 was a factor, we were told that in the problem. We knew when we divided it, the polynomial by the factor, it should give us a remainder 0. Everybody's okay with that? Okay. So what we can say then is my factored form is going to have the x plus 3 in it. Again, I know that because I got the 0. And then my other factor is going to come from the quotient here. So remember, when we write this, we start at the far right. And we have the constant, the x squared, the x cubed, the x to the fourth, x to the fifth. So my other factor here is x to the sixth minus 7x to the third minus 8 there, because, well, we're going to try to factor this now using the factoring tree, and I don't need the zeros there to do that. You could have written them in, but it's certainly just going to make it messier and more confusing looking. They don't really help us any. So far, so good, Megan? Okay. This is a 3-term problem. It's in the quadratic form. Notice the degree of the bigger of the middle one, and the last term is constant, right? And its leading coefficient is 1, so we should be able to do this with the shortcut. So we need 2 things that multiply to give me -8, and add to give us -7. Those things would be -8. And notice that I have x cubed there because the middle term is cubed, right? The middle variable tells you the variables in your factors when you do that shortcut. So far, so good. Anybody else with questions before we keep going, at least at this point? We still have a bit.
I have a question, Mr. Kulik.
Yeah, what's up?
The difference, right?
Correct.
It's just like 0?
Yep.
Okay.
Yes.
Awesome.
Yeah, so 0 times the x to the fifth or whatever is still 0, and then if I add 0 to anything, it just doesn't have any impact. So I just ignored them. Yeah. Okay. So now we have to check the x cubed minus 8 and the x cubed plus 1 to see if we can factor those. Each of those is 2 terms, right? 2-term branch. First thing we check is for a difference of 2 squares. Neither one of those can be, components are odd. The next thing we do is, and they both appear to be a sum or difference of 2 cubes. Both have x cubed on them, so that's a pretty good indicator. The first one, I can rewrite x cubed as x to the third. And I can rewrite 8 as 2 cubed. So when I apply my difference of 2 cubes factoring pattern, in this case, my a is x and my b is 2. So I'd have x minus 2, x squared plus 2x plus 4. And the other one, I can write x cubed as x to the third, and 1 as 1 to the third. 2 cubes factoring pattern is this one, where in this case my a is x and my b is 1. And then I still have that x plus 3 hanging out front. And then if we check these to see if we can do any more factoring, here, I know I can't do anything more with those, so those are done. Differences of 2 cubes. So this is as far as we can go. Megan, did that do it for you? Oh, yep. That would, yep, unrecoverable mistake at that point. But yes, I'm glad that you recognize that you were supposed to put something there. You just chose the wrong number to put there. Good. And this one I think was the most, certainly of those last 4 or 5, this was the worst one. Mostly because the factoring tree part at the end was the most time consuming because you had 2 cube things to worry about, right? which tend to be, at least judging from your homeworks, the more challenging factoring for you guys to handle is when you run into those summer differences of two cubes. Is everybody okay there, Hallie? Yeah. Sure. Sure.
Okay, so that's part of like
Yeah, it's one of those that, like, the better you know it really kind of helps move things along smoothly. I think a lot of times, again, my observation with you guys is that when you have to really slow down and think about stuff, we sometimes get into trouble. That the more quickly you can kind of know what to do next and keep your momentum going, typically the better the things go for you guys. So again, I would give you the factoring tree. I don't want that to be a memorization issue with why you get things wrong. But it's also one of those things, like, the more you really remember what to do next, even without it, I think makes a big difference in your overall confidence and your, the speed which you can do these problems and the frustration tolerance that you have for doing these problems, where you don't feel like you're having to slow down and look things up every 5 seconds, which I know personally, like, can be really kind of tedious and frustrating when you have to do that all the time. We've done a lot of them, so hopefully you're starting to get familiar at least with parts of it, where all you're doing is having to go back and check, be like, okay, do I do this or this next? Where you already have some idea. But again, like, I'd be happy, yeah, I would give that to you to use. Again, the goal would not to be, like, memorizing something like that. I don't think I want that to be like the hindrance as to why you get something wrong. I'd rather have a little memorization as I can, as I can make the test. You know what I mean, guys?
Yeah.
I'd rather have it based on, like, your ability to do math versus memorize some complex chart that we made. Okay. Anybody else? Cool. So today, we're going to take a baby step forward here, or what seems like a baby step forward, and talk about what to do next. That's 7:14. Last night in the homework, you guys did something like this, which was number 5, where you're asked to factor something like this given one of the factors, right? What the next step is, we do if we take away that. So the question we're going to try to answer here is, okay, what do we do if we're not given a factor? Do we just guess at factors and just try them until we find one that works? I mean, naively, that would be what you'd have to do, right? You have to somehow come up with a factor. If you don't have any other way to do it, you'd just be guessing. Does that sound like what we're going to do? We can do a lot better than just guessing, right? We don't want to be guessing infinitely many choices. What we want to do is kind of narrow that guessing game down to where it's not really much of a guess. So that's what we're going to be building towards here over the next 2 lessons. We're going to be trying to keep in mind to go through this lesson. So today and the next lesson is going to be all about how can we figure out what factor to start with. So we're going to start out today, and I want to start by introducing. So we're going to define 4 things here, kind of related. So first thing we're going to do is define a solution. So a solution to a polynomial equation means that if I take that answer and plug it back into the equation, it gives me 0. Right? This is like a concept that you would have experienced in your algebra or pre-algebra class, right? Like probably as you first learning to like solve things like 2x minus 6 equals 0. When you got your answer, your teacher told you to plug it back in to make sure that it still works, to check your work. You guys remember doing that back in like middle school or something? Yes? That's this idea. So if we get an answer, if we can plug it back in and it works, we know that's a solution, right? So even if you randomly guess that number, if you plug it in and it works, it satisfies the equation, we know that's a solution. Everybody's okay with that idea? Okay. So we say that the number a is a 0 to the polynomial function y equals f of x, if and only if, when we plug a into the function, we get 0. You remember back in first semester when we talked about positive, negative, and 0? You guys remember that? That's the same idea here, right? If I plug this value of x in, it should be on the x-axis. We say that a is a polynomial f of x if and only if we can factor f of x into x minus a times some other polynomial. Right? Basically, it's saying that x minus a is a factor of f of x. We okay with that idea? When we say, or the last thing we're going to say is we're going to talk about x-intercepts. So we say that a is an x-intercept if the point a comma 0 is a point on the graph. Now, in a practical concern, or from a practical standpoint, which one of these 4 is going to be the easiest for us to get? Just from a practical standpoint. What do you guys think? Well, the answer there should be the x-intercepts. Because what do you need to get the x-intercepts? You just need to look at the graph, right? Do we have a good way to get a graph? The calculator will generate the graph for us automatically, right? Everybody's agree with that? So what we can do is, if we can graph the thing on our calculator, we should be able to visually identify the x-intercepts. And then because these four things are all kind of related, we can use those x-intercepts then as potential, to create potential factors to do our polynomial division with. Everybody's okay with that notion? Now, what's the catch here? Let's see. Let's summarize this. Okay. So the idea here is that we can use those x-intercepts from the graph to create factors to use in our synthetic division. What are some potential problems with that? Well, for starters, not all of our x-intercepts are going to correspond to linear factors. What do I mean by that? So for example, if we had the factor x squared minus 2, we can't factor that anymore, right? But do you agree with that? That's not a difference of two squares. There's nothing really more we could do with that. But that's still going to create create x-intercepts. Which would be plus or minus the square root of 2. And we can't use that to synthetically divide with because we don't have an exact value for it. Like you're not going to be able to pull off the value square root of 2 from looking at the graph. It's just going to look like 1.4, 1.5 or something, right? So that's a problem. Another example, what if we had the factor x squared plus 2? What does that correspond to? That has no x-intercepts at all, because when we solve that, it gives us an imaginary result, right? Another issue some factors give the same x-intercept. So for example, we had the polynomial x plus 2 times x plus 2. That's going to give us the x-intercept negative 2 twice. Are we going to be able to identify that from looking at the graph right away? So these are all issues that we have, why we need more than just like, hey, look at the graph and use the x-intercepts, right? So there's still some issues here going on. We're going to try to develop some tools in addition to this idea of using the x-intercepts to help limit these possibilities so we know the difference between them, okay? Or know when to look for the imaginary things that we won't be able to see at all. Okay with that idea? So we're going to add in some more tools now. So we're going to look at some theorems now. These are the other tools that we'll use today, and then we'll have some more theorems in the next lesson to kind of round this out, but I can't do it all in one day because it's a lot, right? So the first theorem is called the fundamental theorem of algebra. Which sounds super important, but it's a really simple statement. And the fundamental theorem of algebra just says that every polynomial is solvable over the complex numbers. Which seems like, okay, but that's a super powerful statement. You're saying that any polynomial you can construct has a solution. You can solve it, as long as you allow for complex solutions. They're all solvable. Took a long time for that to be done. That was probably of like the Renaissance era, the biggest question in algebra was to prove this, and it took a lot of very accomplished mathematicians a long time before somebody was able to do this. Although it was inevitable with calculus kind of coming quickly after this. Proving that with calculus would not have been so hard. But without calculus, it was very difficult. What'll be more helpful to us, though, and what we're trying to do, is the corollary to the fundamental theorem of algebra. So the corollary says the number of solutions to a polynomial equation is equal to the degree of the polynomial, provided that you're counting the imaginary solutions and the multiplicities. Now, this multiplicity, this word, is probably not one that we've heard before. But you remember this example that we wrote down earlier where we get the same solution more than once? That's what we mean by a multiplicity. So in that case, we're going to count the solution of -2 as two separate solutions because it occurs twice in the problem. That's all we're saying. So every time a solution occurs, that counts as a solution. If we count them that way, then the degree of the polynomial is equal to the number of solutions. So basically what we've done is we've created a target to know, like, how many solutions should I be looking for right away at the start of the problem, right? So we know exactly how many solutions we should be getting out of it. The next one is called the factor remainder theorem, and this is what we took advantage of in last night's homework when we used synthetic division to do the factoring. That says that And this just says that x minus a is a factor of the polynomial f of x, if and only if f of x divided by x minus a has remainder 0, which is exactly what we've been using when we did our synthetic division factoring last time. We just kind of formalized that. And the last one that we'll look at today is called the rational roots theorem. Oops. So this last one, the rational roots theorem, says for a polynomial f of x with integer coefficients, the rational solutions to the equation f of x equals 0 are of the form x equals plus or minus a factor of the constant term divided by the factor of the leading coefficient. So just to kind of show you how this works. So let's say we have this polynomial. The constant term is negative 35. The factors of negative 35 are 1, 5, 7, and then 35. The leading coefficient is 6. The factors of 6 are 1, 2, 3, and 6. Everybody okay there? So my possible rational solutions to f of x equals 0 are plus or minus. I'm going to have each of these divided by each of these. I'm out of colors here, huh? Let's write this down now, and then we'll color code afterwards. 3 and 6. So I have my factors of the constant term over the first factor of 6. Then I'm going to have my factors of 35 over my second factor of 6. And I'll have my factors of 35 over the third factor of 6. And then I'll have my factors of 35 over my last factor of 6. And let's go ahead and color code this now. Oops.
Mr. Kulik,
Yes.
I have a question.
Yes.
So are you pretty much just putting each, like you're putting each one of the factors of negative 35, you're putting all those numbers over the factors or over the factors of the leading coefficient of 6?
Yes.
So that's it for that step?
Yep.
Okay. Thank you.
You're welcome. Hallie, what's up?
Oh, no.
Oh, okay. All right, so let's put all these ideas together now into like a coherent method, okay? So let's say we're asking us to factor completely x cubed minus 19x minus 30. Notice that I haven't given you a factor where to start with. So what we'll do is we're going to kind of list down the things that we know. So we know that we're looking for 3 solutions, which means at most 3 factors, right? From the rational roots theorem, I know my constant term is negative 30, the factors of negative 30. Oops, forget about 5. Are 1, 2, 3, 5, 6, 10, 15, and 30. But fortunately, the leading coefficient is 1. The only factor of 1 is 1. So my rational roots theorem says I could have plus or minus 1 over 1, 2 over 1, 3 over 1, 5 over 1, 6 over 1, 10 over 1, 15 over 1, and 30 over 1. I didn't bother to write the over 1 part because it just reduces to a whole number, right? Everybody okay there? Why none of those are fractions? I wrote them as fractions up in the example, but it's just cleaner not to write the fraction if you don't need to write a fraction, you know what I mean? Okay. Next, I'm going to go ahead and look at my graph. And what I'm looking for on my graph are X-intercepts that I find on that RRT list. Everybody okay with that idea? So I'm going to fire up my calculator. Okay. So I'm going to go to the first step. I'm going to go to the y equals menu. So the y equals button is in the upper left-hand corner. I'm going to clear out anything that I might have already had in there. I don't have anything in here because I just wrote this down. And then I'm going to type in the polynomial in my problem exactly as it's written. So x cubed minus 19x minus 30. Okay with that? Next, I want to graph this, but I only care about the x-intercepts, and I only care about the x-intercepts that are on that list of possible rational roots there that I wrote down. So what's the smallest value from that list that we wrote down?
The 1?
Well, be careful because they're plus or minus. So the smallest number is negative 30.
Negative 1.
Negative 30 is the smallest. The biggest is positive 30. Everybody's okay with that? So that is, I want the ends of my x-axis to be negative 30 and positive 30. And then the y, all I care about is to be able to see the x-axis. So I just need one y to be negative and the other y to be positive. So I'm going to go to my window and set that to match. So I'm going to go negative 30 to positive 30. And then I'm going to do a little bit less than that. I'm just going to do negative 3 to positive 3 because that'll be a little bit easier to see what's going on, I think, if I'm a little bit more zoomed into the x-axis. But it doesn't really matter. All we need to be able to do is pick out the x-intercepts. Everybody's okay with that? So I'll hit graph and look at my picture. Okay, so it looks like there's nothing going on out here and there's nothing going on out there, but the places where I see it crossing the x-axis, I can't really read what's going on there. So I'm going to zoom in a little bit. So I'm going to go like negative 5 to positive 5. So it's a little bit easier to see what's going on. And now I can actually read what those x-intercepts are. So I have one here at negative 3, and then negative 2, and then positive 5. Megan, what's up? I just changed the window again to negative 5 and positive 5 on the x's. I did the negative 30 and positive 30 to start with, because those were the bounds from my RRT list. So again, it doesn't so much matter what you're picking there. You just need to find x-intercepts. Okay? And once we've identified those x-intercepts, we need to check to see if they are on my list. And I see that all three of them make my list, right? Is everybody okay there? So what that tells me is I can use any one of them to do my synthetic division. It does not matter since they're all on my RRT list. They're all good choices to use to do my synthetic division. So let's do negative 2 first, I guess. So that works, right? Because we got the remainder 0 that we're hoping for. Keep in mind here, why did I put this extra 0 here? because I didn't have any x squareds in my polynomial I was trying to factor. So make sure you're being careful about that. So what this tells me then is one of my factors is x plus 2. I get that because this gives me a remainder 0. If you're like, wait a minute, why is it x plus 2? If you go back and you look at the factor remainder theorem, it's always x minus a. So it's really like x minus a negative 2. So that's why it's changed to positive 2. But just think about it as the opposite sign is fine. It'll always be that way. Everybody's okay there? Okay. And then the other factor is going to come from my synthetic division. Like that. So that's going to be x squared minus 2x minus 15. Again, those numbers at the bottom give me my coefficients. And now I have something that is a factoring tree problem. So I can factor this. It's got 3 terms. Not only is it in the quadratic form, but it's strictly quadratic. This looks like a factoring problem I would have done in first semester, so I just need to find 2 things to multiply to give me negative 15 and add to give me negative 2. How about negative 5 and positive 3? That'll do. And since everything is linear, we would be done.
Mr. Kulik,
Yes, sir.
I'm quite confused on how or why for the graphing part when you got x is equal to negative 3, negative 2, and 5, but then when you did the synthetic division or substitution at the bottom, you got the 1, 0, negative 19, and negative 30. Did you just take, for the synthetic part, did you just take it from the original equation, the x to the third minus 19x minus negative 30?
Yes.
So whenever you do the is that substitution or division? I'm sorry, I'm just a little confused.
So it's the same process. We're using it as division, but it's the procedure is exactly the same.
Right. So in that procedure, do you always use the original equation to put in your values?
As your first synthetic division, yes.
Okay.
So
Okay. Thank you.
let's do another example here where we have to do more than one synthetic division. Okay? Because that sounds like where your head is next, which is good because that's where I want to go next. And that's probably be all that we have time left for in class today. That's okay. Okay. So let's say we want to do this. So how many solutions can we have here? It's going to be the same as the degree for the polynomial. So 4 solutions. What are my possible rational roots? It's going to be the factors of 24 divided by the factors of 1. So the factors of 24 are 1, 2, 3, 4, 6, 8, 12, and 20. To see which one of those factors are going to be the ones that we want to, or that we care about. So I'll type this in exactly as it looks on my sheet of paper. Okay, once I have that typed in, I'll reset my window. So my lower bound for my x's should be negative 24, and the upper bound should be positive 24. I'll hit graph and take a look. So it looks like everything is happening pretty close there. I don't care about anything out here or anything out here. So let's change our window a little bit. So maybe we'll just go -5 to +5 again. And take another look. 1, 2, 3, 4 x-intercepts that I see, which matches up with the 4 solutions, right? Everybody agree with that? So let's see, what do we have? -3, -1, +2, and +4. If I take a look, each one of those is on my list somewhere. So each one of those would be a good candidate to start my synthetic division with. So let's just pick one of them to use. I'm going to pick -1 because it makes the arithmetic the most. So we'll start our synthetic division. No starting values in my synthetic division are just coming from the coefficients of the polynomial I'm trying to factor. So we'll do our synthetic division. That worked. So what we have then is x plus 1 as one factor, then x cubed minus 3x squared minus 10x plus 24 is my second factor. But notice that x cubed minus 3x squared minus 10x plus 24, if I tried to factor that with the factoring tree, I'd use grouping because it's got 4 terms. But grouping's not going to work on that. You could try it, but if you look at the 2 groups, the first group, the leading coefficient would be x squared. The second group, the leading coefficient would be 2, and you aren't left with the same thing after you take those GCFs out. So we'd have to do another synthetic division. So what am I going to synthetically divide? I'm going to do another synthetic division, but I'm going to use what we got. Yes, Megan? Well, if you tried to factor by grouping, it's not going to work. So it's 4 terms. That would be the factoring tree method you'd use. You can try it, but you'll find that like when you take you make your 2 groups and take out the GCFs, the pieces that are left over don't match. So there's nothing more. You can't do factor by grouping with it. So we're going to do another synthetic division. Okay, so we need to find a factor for x cubed minus 3x squared minus 10x plus 24 to try. So we'd have to start that whole process all over again, right? Wrong. Wrong. Because any factor that worked for the original polynomial, the factors that are left would work for the remaining part of the polynomial. You know what I mean? So the factors that we'd have left to try for that are -3, 2, and 4. So I'll just pick one of those. I'll say 2 for the sake of argument. So that worked. So the x plugs down. We have an x minus 2, then x squared minus x minus 12. And that piece, the x squared minus x minus 12, we can deal with, right? That's something that looks like a chapter 4 problem that we would have done in first semester. We just need to find 2 things that multiply to give us -12 and add to give us -1. That would be -4 and +3. And since everything is linear, I know that I'm finished. Now this is a lot. I recognize this. We're going to be spending a bit of time here and giving you an opportunity to practice this. This is not a trivially easy skill, right? There's a lot kind of going on. Once you get the hang of it, it's not so bad. But it does take a little bit of practice, and there's a lot of skills involved here, right? You have to be able to use the factoring tree. You have to use synthetic division. You have to use all these new little tools to figure out, like, what even to use the what factor to use to do the synthetic division. So there's a lot going on. I understand that. Okay? We're going to, next class, we're going to add in some more tools for, like, when weird things start happening. Believe it or not, nothing weird has happened in any of the problems I've given you as an example. And that'll finish out this factoring method for polynomials that we're going to deal with at least. And we'll spend some time practicing that. And then there's a little bit more to do in this chapter in kind of going in the reverse direction. So if I give you some solutions, can you build me a polynomial out of that? And that'll be the last topic for this chapter. Okay, but we'll take some time. We'll take at least one day in there just to do some practice in class, particularly dealing with this method since it's kind of tying everything together and it's got a lot going on. For next time, for your chapter or for your homework check on Sunday, I'd like you to do this chapter 5 homework. So this is doing exactly what we did in these last two examples that we did today in class. So I ask you to kind of show all the little pieces of information that I showed when we did the examples is basically what all that direction is saying. Okie dokie.
Thank you.
You're welcome, guys.